Muy buenos días a todas y a todos. Gracias por estar aquí. Supongo que hay muchas conectadas también en YouTube. Tengo el gran placer de invitar y presentarles al doctor Lacanna y luego estará el doctor Giacomo Olivieri. Ambos vienen de la Universidad de Florencia, en Italia, en particular en el Laboratorio de Geofísica Experimental. Y pues ambos traen varios años, muchos años de estudio de los volcanes activos, en particular con redes geofísicas, y el día de hoy están aquí para apoyarnos con un proyecto de monitoreo del volcán Popocatépetl con infrasonidos. Entonces, las charlas de hoy se van a enfocar en los infrasonidos registrados en los volcanes. Y todo este trabajo ha sido desarrollado en grupo con Maurizio Ripepe, no sé si algunos de ustedes lo conocen, que espero que nos está escuchando en línea también para las preguntas. Y pues ya, sin más tardar, gracias por su presencia y adelante, Giorgio. Gracias.
Gracias, Sebastián, por to invite me for this seminar, for this interesting project on Popocatépetl. Sorry for my pronunciation. So my presentation is about, its title is Eruptive Source Parameters Derived by Infrasound Signal. As you know, the source parameters, the main of the source parameters is volumetric flux related to the volcanic eruption. The volumetric flux, bigger, larger it will be the volumetric flux, bigger it will be the index, volcanic explosive index, and bigger it will be also the plume height. In this case, you can see how the plume, the volcanic plume can go up to the level between stratosphere and troposphere. The red arrow indicates the aircraft flight altitude. So in this case, the flight and the aircraft can be intersect the eruption and the ash plume, which also with the explosion lower than a volcanic explosive index, lower than 4, can reach 20 kilometers, and so can be upper than the altitude on the flight. If we compare the global flight path, the white line, and the red dots are the active volcano in the worldwide in the past 10,000 years, you see how a lot of the global flight intersect the active volcano into the world. For this reason, it's important to know where the volcanic ash is, and in the last 60 years, more than 94 encounters of commercial flight between 1953 up to 2009, and 2 of them were damaging per year since 1976. For this reason, for aviation, it's crucial to know where the explosion occurred, when occurred the explosion, and how big it is, this explosion. Usually, the volcanological observations are based on satellite. With satellite, you have the low acquisition rate, low information rate, but it has a coverage, it's a global coverage. In the case of seismic, geochemistry, and GPS, you will have a high rate of information, but the coverage is strictly limited to the volcano. This is completely local or very local. In the case of the infrasound, you have the high rate of information, and the coverage could be from local, regional to the global. This is a case of the eruption in Iceland. The eruption in Iceland was detected by several infrasonic arrays far away from the volcano. And this is the red one is the pressure detected by the array located at only 8 kilometers far away from the source. And the blue one is the detection of the eruption detected at 2,300 kilometers far away from the volcano. And you see how the pressure, same variation of the pressure detection, of course, with different amplitude, but the same variation to the array located close to the source. And now, what is the infrasound? The infrasound is the acoustic pressure wave propagates in the atmosphere with the same velocity of the acoustic wave, with the velocity of 340 meters per second. Of course, the velocity of the infrasound depends by the temperature of the air, and the only differences with the acoustics is the content frequency of the signal. For the infrasound, the content frequency is below 20 Hertz. For the acoustic wave, is above 20 Hertz. The infrasound we can approximately is like our sound, our voice. So the sound is generated by the flow air emitted by our lungs. Then when this variation of the flow, the air flow generate the pressure wave, this is the signal just close to the mouth, our mouth. So, and you see the pressure wave close to the our mouth is proportional to first derivative of the volumetric flux, the Q. And this is the Q emitted by our lungs. For volcanic acoustics, this is the pressure wave generated by this is a typical strombolian explosion. In linear acoustic pressure, the pressure of our signal that we recorded at distant from the source is proportional, depends by the volumetrical flux, is the first derivative of volumetrical flux by density of the air and the distance from the source to the station. And volumetrical flux is the multiplication about the area of the conduit and the velocity of the gas expansion into the conduit. So we have the eruption type, which is defined by the VEI, the VEI, which depends by the plumite. The plumite depends by the volumetric flux, and the volumetric flux is possible to estimate using the pressure, acoustic pressure propagates from the source to the station. But the pressure wave, during the propagation, to correctly estimate the volumetric flux at the source, we have to correctly estimate the pressure wave at the source. The infrasound propagates in the atmosphere. So the atmosphere, we can consider it as a perfect elastic medium, because at the low frequency, the absorption effect coefficient is extremely low. And so the infrasound propagates for thousands of kilometers. But the atmosphere is not static like the ground, but is dynamic, changing the velocity of the wind, the direction of the wind, the temperature profile, and this changing is during the day, changing in the time. And for this reason, the dynamic and the changing of the dynamic properties of the atmosphere affect the infrasound propagation, which has to take in account to properly assess the correct pressure at the source. So the infrasound is affected by the atmospheric structure, but it also affected by the attenuation of topography, diffraction by the topography generated like a barrier, and by the vent geometry. Starting for long infrasound propagation, this is the case on Sakurashima volcano. Sakurashima volcano is located in southern part of Japan. We install, yes, the infrasound network, which consists in 15 stations, and 15 stations were located from 3 kilometers from the source up to 60 kilometers from the source. This is the waveform for 3 types, where every type has a different day, and in different days there are atmospherical properties. By numerical modeling of the infrasound propagation using fine difference time domain, you can see how the wind direction and the velocity of the wind can affect and distort the wave field. In this case, we have at 10 kilometers, we have 40 meters per second at this elevation, and you see how the amplitude of the wave field propagates in the same direction of the wind is larger than the other side of the wave field, which propagates in the opposite direction of the wind. Okay? So, and the wave field is modified, and the wavefront is bended by the wind. The other main effect is the topographical attenuation. You see, this is the position of the source at Sakurashima volcano, modeling the infrasound propagation. You see how the wave field beyond the topographical barrier, the amplitude is strongly attenuated than the station located just in line of sight of the source. Okay. And the attenuation of topography can be induced at the reduction of the amplitude, 1 order of magnitude of the attenuation. In this slide, I will show how both effects combine to give an amplitude distribution. So this is the Sakurashima, Kirishima, Keimondake. We have 120 kilometers of our propagation. In the top plot, we have the no topography, and this is the atmosphere, is the infrasound amplitude distribution induced only by the atmospherical condition. We have the red, white, this is the wind, propagates towards northwest, northeast, and you see how at 10 kilometers, and 5 kilometers, below 5 kilometers, the wind propagates in the opposite direction. And you see how the amplitude distribution is strongly affected, depends by the wind velocity and direction of the wind. The middle plot is the static atmospheric, the property is static, so we consider the atmospheric as a static, without wind, only for topography. This is without topography, this is with topography, but no wind. And you see how also the amplitude distribution is completely modified by the topography. In the northeast part, where the points are in line of sight with the source, we have larger amplitude than the other point located beyond the topographical barrier, and there is a modulation, a sort of the modulation of amplitude distribution. The last plot, the bottom plot, is the combination of the both effect. So using the correction factor by numerical modeling, we can estimate correctly the pressure at the source. This is the correction using geometrical spreading, normal decay with the distances. And you see how the amplitude at all of the station is spanning in a range of more than 30 dB, more than 1 order of magnitude. When we using the factor, the correction factor, estimate by numerical modeling, which including attenuation by topography, wind effect, and the normal decay, the error strongly decrease. Okay? In this case, we can reach, we can estimate the pressure at the source. When we arrive at the source, we have other two main effects. One main effect, which is induced by the open vent. So we considering, the gas expanding into the conduit and propagates into the conduit, generated a plane wave. When the pressure wave reached to the open vent, part due to the impedance contrast of the open vent and the atmosphere, part the energy is radiated outside, a part of the energy is reflected back into the conduit. So we have to know which is the quantity of the energy, of the amplitude is radiated outside, because our sensor is located outside of the vent, not in the conduit. This is the important, because if we can install inside the conduit the sensor, this problem could be avoided. And for this reason, we have to know which is the pressure radiated outside. And in this case, the main parameters are represented by the reflection coefficient at open vent, which is defined like a ratio between reflected pressure and the incident pressure. And using the formula proposed by Norris and Cheng, and also validated by the numerical model, you see how the reflection coefficient depends by the key, the wave number of the source key, and the radius of the vent. If the Ka, the multiplication, so the Ka is smaller, so the wave number is much larger than the radius of the vent, the reflection coefficient is close to the 1. So most of the energy is reflected back into the conduit. Contrary, if the Ka increase, most part increase the quantity of the amplitude radiated outside of the vent. And so it's important to define the coefficient of the reflection, which depend by the source, so the frequency of our source, and the radius of the conduit. The second effect induced by our conduit is the radiation pattern of the acoustic wave. In this case, we have a simulation for 3 different cases. For 3 different cases, we have the same frequency, 4 Hz, for the A, B, and C. The last thing that is going to change is the radius of the conduit. In this case, is 3 meters, 15 meters, and 30 meters. When increase the Ka, we have a larger quantity radiated outside, but we will have also larger directivity. The radiation pattern, it will be more the larger amplitude is located just up to the vent and not onto the ground. Also in this case, we have the sensor not in the air, but on the ground. So we have to know which is the radiation and the quantity of the energy propagates onto the ground. Okay. For this reason, we use the volumetric, the pressure wave. This is the pressure wave that we recorded. The integration, we can estimate the volumetric flux inside of the conduit, considering the waveform that we recorded, which is located at distant, R is the distance from the source, and taking in account the topography with insertion loss, so the quantity of the amplitude is attenuated by our station and the source due to the barrier, the topographical barrier. Then the reflection coefficient, which depends by the wavelength of the source and radius of the conduit, and the directivity. So we correct the acoustical linear propagation using this correction: insertion loss, reflection coefficient, and directivity. So when we have this information, these parameters, using infrasound signal, integrate the waveform, this is the integration of the our waveform, we can estimate the volumetrical flux from infrasound. Assuming the vent radius, we can estimate the exit velocity, assuming the duration of our signal, the total volume, and assuming the density, also the total mass. Of course, the hour parameter that we can extract by infrasound is the volumetric flux, okay? Is the volumetric flux. Now, so this equation is robustness, is valid. So, and we compare the volumetrical flux and the other source parameters derived by infrasound. We compare with other independent observation. For Stromboli, we compare with gas flux. With the Etna, with the radar, as well as for Eyjafjallajökull, for Kopaue with visible camera, and with Popo, the recent work with Sebastian and Santiago, with the satellite. Okay, starting with Stromboli. Stromboli is over 2 years of the infrasound data and gas flux. The black one are the volumetrical flux estimated by using infrasound, and the magenta is the volumetrical flux estimated using SO2 camera. Over 2 years, we have the same variation, but it's important to know, to see also the magnitude of the volumetric flux is the same. And this tell us the infrasound is an indirect measurement of the gas flux into the conduit. So for Stromboli, we have a good correlation. Okay, like for Etna, this is the thermal camera, this is the seismic signal, and this is the energy of infrasound. Etna, like a Popo, generate a lava fountain, and when you have the increasing the thermal radiance of the lava fountain, as you can see now, we have an increasing of the seismic signal, and also we have an increasing of the energy of the infrasound, and the plume height reached the maximum height. This is starting like a Strombolian, and then we have the big lava fountain, and the plume height will reach 4 kilometers above the vent. Also, in this case, we estimate volumetrical flux using infrasound, and then we compare the exit velocity estimated with the infrasound with the radar. So also in this case, we have the same trend, and also the value, the magnitude of the exit velocity is more or less the same, around 200 meters per second. For Kopaue, we install in Argentina, we install infrasonic array. We detect several events. From infrasound, we estimate the acoustic exit velocity, which in that period when the array was working was extremely low. We estimate velocity around between 10 and 15 meters per second. And analyzing also the wind velocity in that period, you see the wind velocity was around 15 meters per second, a little bit much larger than the exit velocity. And this is supporting the information with visible camera, where the plume bending immediately just above the vent. So the exit velocity was lower than the wind velocity. This is the only information that we had from Copaue. And then this is Popo. Popo we compare with satellite. Also in this case, we estimate the volumetric flux with the infrasound. And then with the satellite, estimate the plume height. In the case of, this is the primary result by Santiago, this is the correlation, the Mastin equation, which correlated the height of the plume with the volume erupted, and the star, this is are the 15 eruption event detected in 6 months, 2023 at Popo. And also in this case, we have a good correlation between the information retrieved by satellite with the information derived by infrasound. But in the case of the Eyjafjalla Jökull in Iceland, sorry, but also we estimated the volumetric flux, the mass flux, the red one using infrasound, and the plume height is retrieved by the radar. You see how just below, before 16 May, we have an anti-correlation between the volumetric flux and the height of the plume. Did the correlation increase only when in the model we include to retrieve the height of the plume in the model, we considering we including the wind field and the temperature profile. This is the height without wind, just from infrasound, and this is the red one is the height of the plume derived by infrasound but corrected by the wind. In this case, the correlation is much better, because in this case, the infrasound information derived by the infrasound has to be considered as the input parameter for numerical model or for model for dispersion, ash dispersion. Concluding, we can see elastic properties of the atmosphere allow infrasound to propagate over long distances, making it a powerful technique for monitoring volcanic activity. The volumetric flux estimate from infrasounds must take in account the propagation effect, atmospheric properties, topography, and vent geometry. A good correlation is observed between SCP derived by infrasound if we compare with the other independent observation. And then the compares confirm the reliability of infrasound with the advantage to get information in real time, like seismic, deformation, and so on. Thank you very much.
Muchas gracias, Giorgio, por la presentación. Vamos a seguir directamente con Giacomo y luego las preguntas hacemos todo junto.
È più comodo con questo. È comodo con questo. Con questo, sì.
I want to say thanks to UNAM to invite me here for this talk, as well as I'm very happy to be involved with Sebastian Valad in the project of Popocatépetl. And the main topic, after the good presentation of Professor Lacanna, the topic of my presentation is regarding the early warning system using infrasound. It's not for calculation related to the amount of ash or the amount of energy on the atmosphere, but is just how to use infrasound to quickly inform or forecast incipient eruption. I will present the case study of Etna volcano. So this one is okay. So just a summary. There is a brief introduction, then some basic principle about the technique of using infrasound as an array of sensor instead of single sensor, and then some of the result of the validation of the early warning system at Etna, as well as performances in terms of false alert rate or true positive counting or score, sorry. So as Giorgio said, what the main topic is how to detect volcanic ash on the atmosphere, because this could cause failure of engine, as in this case in 1989 for the fly through the Redoubt volcano in Alaska, which experienced, I think, half an hour or maybe less of no working engine. And so it is important to understand before if we are going through this type of risk. And of course, this risk is related to safety, of course, but there is also an economic loss related to this type of risk. As Giorgio said, there are several types of observation of eruption, and satellite, of course, is a global cover globally all the active volcano worldwide, but the rate, so the velocity to have information in real time is not so high because the satellite is passing, the passage of satellite is not quickly. And among the other seismic, geochemistry, and GPS, I'm going to present the infrasound observation type respect to the other. So just to say at the beginning that this is the first case of an infrasonic early warning system used for operational purpose. And this is the Nature magazine, which dedicated us to this project, started in 2007, if I will remember, dedicated us a magazine related to this first case study worldwide. So, array technique. So, in order to, let's say, reliable monitoring and measuring the pressure wave on the atmosphere, we use an array of sensors. Array means more than one sensor, at least 3 sensors, deployed in the ground in a particular geometry. But let's say for volcanic application, the dimension of the array is 100-meter aperture. Here you see a scheme of an infrasonic pressure propagating in the atmosphere, and this is the records at the array. And due to the fact that the velocity is 340 meters per second, the arrival time of each signal at the different sensor is different among the sensors, but due to the fact that the attenuation and the frequency, the low frequency of the pressure wave in the infrasonic wave field bandwidth is the shape of the signal is the same at the fourth sensor of the array, but the arrival time is different. Okay, based on this delay time, it is possible to calculate the provenance of the sound. And this is a key factor in order to discriminate different type of sources, because not only volcano emit infrasound, also airplane emit infrasound, avalanches, as well as many other type of source. So using array allow for let's say, to have some wave parameter which are very important in terms of algorithm in order to discriminate different type of signal and have more robustness in terms of software or computation. Okay, this is the example of Etna in terms of setup. Here is the volcano, almost 3,000 meter elevation, and actually to date we have two systems at distance of 5 and 6 kilometers and 6 kilometers. System are during the years we experienced two main type of array equipment. One is based on copper cable. The laser is okay. The classical way is to use copper cable sensor, data logged and power provided by solar panel and battery, and in order to transmit the data, the cell phone communication. Since 2021, we are testing a wireless array, so without any cable, using a 2.4 gigahertz transmission between the sensor and the wireless receiver. And currently, this system is wireless, and the other system is cabled. Here is an example of the infrasound signal recorded during a lava fountain. So basically, here you can see, Here you can see the seismic, just for comparison, but here in blue is the waveform during, let's say, 6 hours in terms of time, and this is the mean pressure associated to the infrasound signal, which is this one. So the seismic and infrasound share a common shape. So what the seismic record and the infrasonic signal is recording the same phenomenon, such as the lava fountain. But it is important here to distinguish between two main phases. One is related to the initial stage of the lava fountain, which is characterized by strombolian activity. Often is very violent strombolian activity, very frequent. Every 5 seconds you have a strombolian explosion. And this phase, in terms of regime, is a slug regime. So there is a rhythm. One explosion, then another, and then another. And this is the first regime, very important for forecasting application in this case. And while starting from here, the pressure increase, but it is increased and the regime change because the signal here is different from here. Here the signal is continuous pressure oscillation without any sudden transient as in the previous stage. And here is the difference from thermal camera. This is the phase 1 and this is the phase 2. And here there is the gas thrust which is oscillating, and this is the beginning of the fragmentation of the magma column, which then produce the ash on the atmosphere. In terms of computation, we use a simple parameter, which is the named infrasonic parameter IP. And this IP is just the mean pressure for multiplied by the number of detection. So here again the time, here you have the number of detection per minutes, and here you have the back azimuth, so the direction of provenance of the infrasound during lava fountain. As you can see, during the phase 1 stromboli activity, you have discrete pulses, and so the number of detection reach a peak of 30 per minute, while when you have the main energy emitted by the infrasound energy emitted by a volcano, so the number of detection is continuous. Okay, so this is one of the parameters included in this, let's say, early warning main parameter. Of course, the signal has to be equal at all sensors, and this is the semblance parameter. So semblance larger than 0.5 means that I'm detecting signal, it is not noise, and it's a powerful parameter for reduction of false alert. And using the back azimuth, we focus the calculation of this parameter only in the azimuth range associated to the active vent of Etna volcano. So this is another constraint in the main, in this IP infrasonic parameter. So in general is the whole infrasound energy emitted by volcano from active vent. That's the meaning of this simple parameter we use for early warning purposes. Here is an example of EP parameter during a lava fountain episode on March 2021, and the early warning system use two simple EP threshold. One is related to the first, one is capable to detect when the stromboli activity reach a level of violent stromboli activity, and the other one is a simple threshold, fixed threshold, who indicate that we are going through different regime related to lava fountain. And these two simple threshold was fine-tuned using several 38 lava fountain episode where these shapes like rampa, so increasing infrasound energy during time, is shared by most of or all lava fountain episode. That's why the thresholds are very simple. There is no other parameter used to discriminate between these two different stages of lava fountain. And so in terms of alert, the EP threshold must exceed the threshold for at least 5 minutes, and this reduces the spike on the signal related to the single big explosion, for example. And the main parameter of this, the most important threshold of this parameter is the threshold related to level 1, so this one, because these allow to anticipate the probability to have ash on the atmosphere. So the stromboli activity is or the level of stromboli activity is the pre-warning. Okay, we don't know if will be followed by lava fountain and ash in atmosphere, but in order to forecast, we need the main purpose of this algorithm is to anticipate possible lava fountain in the future. So it's a forecasting, it's not a nowcasting. And this is the main or crucial parameter. And in this example, we start, this is the flow chart. In the flow chart, there are EP value, different EP value related to different early warning level. So there are a level related to the system is not working, and this is another important information for early warning purposes, and this the EP is equal to 2. If there is no activity, the EP is -1. Instead, if we detect activity but low with an EP value lower than 60, this is ordinal explosive activity. The color code is yellow in this case, and the AW level is 0. And this is the time at 10 in AM. And here the infrasonic activity started to increase, but the level is not so high. When the system, when the EP parameter exceed the first threshold, the color code in this case is orange, and the level is EW1, and then EW2 when the EP parameter exceed the second threshold. And at the end of the lava fountain episode, we provide notification on the activity went back to the normal. That's the flow chart of the early warning system. Of course, all this information are provided by SMS and email, so quickly, and the algorithm work, of course, 24 hours by 7, and provide automatic notification. This is another important issue, because communication with civil defense in order to have action after the early warning notification is a very important step in order to inform aviation, in order to inform people who stay visiting the Etna volcano, because there are a lot of tourists which go up to, I think, 300 or 200, maybe 200. And the most important aspect of the early warning system with respect to normal bulletin or communication by phone is that the algorithm automatically inform directly, can inform directly the municipality as well as the Etna guys, so people who are in charge to manage the risk. And that's the another, let's say, not secondary aspect or powerfulness of automatic early warning system, and in the specific case of Etna, for this one. So what about performances? Here is the performance are updated, and considering 122 lava fountain episode from 2011 to 2024, the system was providing 141 alerts, and when I say alert is AW1, so the forecast alert. So that's the performance of EW1, the forecasting performances. And in this dataset, we have 98% of true positive rate, and we have false positive rate. So true positive rate means the system was sending an EW1, and after some period, there was a lava fountain. While false positive ray means that the system is exceeding the first threshold of EW1, but afterward there will be nothing. So the strombolic activity was not followed by the lava fountain. And then we have some false negative related to strong wind. False negative means that there was a lava fountain, but the system was not sending any alert. And mainly these few percentages are related to strong wind. And currently we are working to find out some places where we can reduce the effect of wind, for example, forest, but it's not simple for many other reasons, installation, presence of communication system, and so on. So at the end, the system was performed very good at Etna volcano. In terms of forecasting, what does mean? Forecasting means before the risk occur. And in average, we have 1 hour of pre-warning using, again, AW1. But there are some phenomena, some episodes of lava fountain which start in Strombolian and then change suddenly in few minutes, 15 minutes or 10 minutes to lava fountain. And there are also the other cases where the system is exceeding the AW1 threshold, and then after several hours we have the lava fountain. But this type of latency, let's say, or the forecasting time, the average is useful or is enough for aviation, for example, because I think for aviation, because the main information provided, what the aviation can do is to change the route of the flight, depending on where the ash is going respect to the weather condition. So if you join this information to weather conditions, you can forecast where the ash will be. So then the aviation agency can manage in order to land on Fontanarossa Airport on Catania, passing from east instead of west, but the agency, I think, so you cannot inform the pilot in few minutes before the ash on the atmosphere, because it's not possible to change like a car the path in few minutes. If I will remember, in order to change the flight, the procedure requires 15 minutes. So this type of statistics in terms of time of forecasting are suitable for this type of application, not in all cases, of course, but in general, the statistics say that this forecasting time is proper forecast for aviation application. So we are looking for to use the experience gained at Etna volcano to calibrate and for the robustness of the equipment on Popocatépetl volcano. I'm very happy to go there, I hope tomorrow, with a good team, I saw. And of course, it is necessary to calibrate and optimize this general algorithm used operationally at Etna for a different case study, so different distance, different type of activity. So it should be important to, in order to have a final product, it is important to calibrate year by year, but again, the experience gained at Etna volcano will be, so it's very important to reduce the time of calibration, in my opinion. Thank you.
Muchísimas gracias, Giacomo. Gracias, Giorgio. Si hay preguntas, primero en la sala. Uno aquí.
Several questions, but okay, and even curiosities anyway. Okay, the first one for Giorgio, no? You showed the numerical modeling, no, that affects, of course, the wavefront, okay, of the acoustic emissions, no, and then it affects also the arrival time, I think, okay, because you showed, of course, the amplitude of the wavefront, but I think also the arrival time.
Of course, because
Okay, and this is accounted, I think, in your integration, and when you showed a stacking of several waveforms, no?
yes.
Okay, and you fit with the cross correlation, I think, or something like that. How do you fit the maximum peak to make the?
Of course, the main thing as Giacomo showed is using the array, because the array you fix, the velocity remain constant along the array. Okay, and this is there is no, you have the changing of the velocity of propagation during the year. No, this is the source is the same, and you have of course you have the changing
Because of the wind.
because of the wind.
Okay.
But in this case, but if you have them, if you have the array as Giacomo showed is 100 meters.
No, the difference in times are really, really short, and then of course you can.
But so you have changing in the arrival time, but also the changing is in the amplitude.
The main factor for you is the amplitude.
Yeah, because you are using the amplitude, modeling the wind and the attenuation of the absorption, you can estimate the correct factor to assess the pressure at the source. Okay? Because with the array, I know the sound coming from that volcano.
Yeah, the source,
this is
the
big power of the array. Okay, because I recognize that direction there is the volcano. I know it's coming from that direction, and I know that waveform is related to the volcano.
Okay. Thank you.
Thanks so much. I have several questions. The first for Giorgio, just a very general one, but you show several case studies, Stromboli, Etna, Copawe, Popo. The general question is, how about the specific volcanoes condition, such as magma properties and magma compositions in every kind of different activity affect the calibration and correction coefficients?
Okay, the assumption of the infrasound is generated by the gas expanding of the conduit. So because the main factor, because if in the magma there is no gas, there is no explosion. No, there are like in Martini. Party, no party if there is the martini, no? And you can do the party if there is the gas. So the main thing is the pressure wave into the conduit is generated by the gas expanding into the conduit. Then you can change the quantity of the water, the composition of the magma, could be different, but the main assumption is the gas is expanding. Probably we can have changing in frequency in the waveform could be different, something like that. But the main assumption is the gas expanding in the conduit and compriming the air into the conduit and propagates in the atmosphere. This is the main. I don't know if I replay your answer, because you meaning there is the volcano has different composition, different behavior, but in general can induce no explosion. Also, no, with more or less the period, the frequency could be different. But if you start from the assumption that the infrasound is generated by the gas expanding in the conduit, you can waveform differently, but in any case, the main source is volumetric flux expanding into the conduit. This is the main assumption, yes, but this is a good answer.
Thanks. And another question to Giacomo about Etna. If I remember correctly, in the last years, in 2021, Etna was producing a lot of fountains, like trains of fountains, no, with some period, one every 2-3 days, if I remember correctly. So just a curiosity about the efficiency of the algorithm. What about if there is a train of lava fountain? So the EVU stays at level 2, or it goes down and then it came back again? Or what about if we have a period with a lot of events, one after other?
I understood perfectly, and this is a good question, because sometimes there is 2 lava fountain and there is no decreasing up to EW0, okay? And for algorithm point of view, you need to not only an increasing threshold criterion, but you need also decreasing threshold criterion. So you do need to contemplate that we are on AW2, and then the energy, infrasound energy, go down to EW1. And in this case, you can also discriminate between 2 lava fountains at few hour distance. Okay. Otherwise, so this is first, but consider that for simplicity, once you are in EW, all the action are in this type of scenario. So you don't need to discriminate 2 lava fountain for civil defense purposes. Okay, of course, it's a good question, because the algorithm currently has no this decreasing threshold level, but it is possible to implement. We need several cases in order to fine-tune the code. At the moment, we use 4 hours of activity below EW1 in order to re-zero the level, okay? So the strategy in this case came from a civil defense point of view. Once you are in EW2, you are in a risk scenario, we can wait in order to reduce to EW0. While during the onset, civil defense asks for, say, tell me as quick as possible if you can forecast something in the future. But after all, for civil defense point of view or purposes, is not a big issue, the one. It's a big issue for me, which are in charge for the software, and for you, which maybe you can have a look to the dynamics. Because 2 lava fountain in few hours, of course, has some relevance in terms of interpretation of
yes.
specific lava fountain areas.
Yeah, for sure. Thanks.
Yeah, thanks a lot. Very interesting. I saw with the sorry, I can't remember your name.
Giorgio.
Exactly. Giorgio. In several equations, you had the conduit radius. I know that's not something that it's very easy to constrain. So how sensible are your models, or how do you do to constrain that?
No, this is a very good question, because the main problem is to define the radius of the conduit. In general, we link to the bibliography or to the work, and we estimate in the case of the Etna, it's possible to see the conduit, the radius with the drone, but in any case, yes, the main constraint about volumetric flux, no, because usually the wavelength of the signal is much larger than the radius. And in much of all of the example that I show, the Ka is smaller than 0.5. So we have the wavelength is much larger than the radius. And that case is easy. There is a small variation of the volumetric flux changing the radius. The main constraint is when you estimate the exit velocity. Because when you have the volumetric flux and because the radius, the surface of the conduit, you have the radius elevated to 2. So, and this is implicate a big problem, you have large variation when you use the different radius. Because usually the wavelength, the frequency, of the signal the volcano that I show, they have the frequency much larger, or better, the wavelength of the signal, infrasound signal, is much larger than the radius. So you more or less you have the radiation pattern is main of the case isotropic, but the velocity is much more sensible to the radius. That's a good question, yes. Because is more reliable the volumetric flux than the exit velocity. And the volumetric flux this is a point. Volumetric flux has to be the input for numerical model for harsh dispersal, or not numerical, or empirical model, including the wind and the atmospherical properties.
Gracias. This is a question for Giacomo about the early warning system. Is this advisory only provided for the airport authorities, or for the authorities in general, or also for the public in general?
So during the initial stage of say design and develop a system like that was for national civil defense, so mainly related to aviation.
They pass it to the public. The question is, how do they take it? For instance, you show that you have a 97.5 rate of accuracy, and sometimes for aviation, as you correctly said, it takes money to tell them that they have to change the trajectory of the plane, or to do a notification. If it's an international airport, it requires to do an international notification to all the airlines that are flying to that particular airport.
Correct.
And the question is, they don't like that, because there is an uncertainty, and the uncertainty for them means money. How do they take it?
Yeah, so we provide this information to the National Civil Defense, which then provide the information to, or propagate the information to world aviation agency worldwide. So
they decided.
Yeah.
I mean, if it's good,
it is not
you don't
so
get the credit.
It's a very important part of the early warning application in general. It's not for volcano, but for every early warning application. So the other application is for mountain guide. And so local municipality, which is in charge for the civil defense of the municipality, could use early warning system. But at the moment, I think Gianfranco is the mountain guide here who works on Etna for rescue, and I think currently is not used by the municipality. Or
No, it is.
because also there is a problem in order to what you have to communicate and what people have to do after the communication. And when you have a fast communication, you need to have a fast action. So before the final user, guide or people, community can use an early warning system, that it is necessary to have a training on how to use. And that's why I think that it is a complex issue, but I think the national agency with the aviation agency is more easy that are the organization to digest such quick information in order to have the right action, instead of for local application, there is no training of the person, and the municipality, which is in charge for the local civil defense, is not ready at the moment to use such fast information.
Thank you.
Sí, thank you very much for these very nice talks. I have a question and a comment for Giorgio.
Please.
One was rebounding on Marine Oil's question about modeling the infrasound source as the opening of a conduit with a specific radius and impedance contrast. What if the source is not an open conduit but a closed conduit, which is just bursting? That was the first question. And the comment is, you show results from Copawe. I record some videos of the interior of Copawe crater that shows the radius of the vent, and you can calculate also the exit velocity. So if you want, I can give you then, if you want to compare with your predictions.
And we have also the infrasound signal.
At that moment. But I don't know what was the period where the...
I installed the infrasonic array. I have to check, but it was around 2017, 2000.
No.
15. No, about the open conduit or close. So we like when the conduit is open. No, in general, no much infrasound is generated by the open vent volcano. Mm-hmm. And in that case, I show the volcano is generated by open vent volcano. In this case, of the same example. You mean it's close like Montserrat, for example?
Or like many volcanoes that generate Vulcanian explosions. Popocatépetl might be one of them.
Yes. In that case, probably, and also one assumption is in this case the propagation and the source is a Mach number lower than 1. So we have the velocity of the gas is not exceed the acoustic velocity. So we are not a supersonic condition, but in low Mach number. And probably in that condition, you have also the effect by nonlinear of the acoustic propagation, or you have a large mass, probably like a Montserrat, where induced gravity wave oscillation of the whole of the atmosphere. In that case, the condition in the atmosphere, the propagation and the source dynamic, it will be different, like also at Popo, no? When we record at 5 kilometers, 7 kilometers, they recorded almost 5 Pascal. No, with that 1 kilometers correspond to 35 Pascal. In Strombolian eruption, we record this kind of the value, and the most of the infrasound is generated by low pressure. It probably is indicate, the escalation of the eruption, like occur in Etna, and probably this is the best precursor to define when the eruption is going on. And in this kind of the regime, with the acoustic linear, we are able to model the volumetric flux and the source parameters which generated the eruption.
Any more comments online? Maybe one quick comment from my side. Indeed, the data that we have analyzed in a preliminary manner with a temporary array on Popocatépetl was during 2023, and this was maybe a very specific type of activity for Popocatépetl, which is not so common. And it was very similar to the activity of Etna, meaning continuous slug bursting and eventually maybe small lava fountain. Maybe the term may be a bit difficult. But overall, generally Popocatépetl is more accustomed to ash emissions due to volcanic explosion.
Okay.
So this will be interesting that we started adapting the code that Giacomo presented and developed. We started adapting it. It worked well in 2023. Now, if the behavior of the volcano switches back to its traditional system, then we might have to perform other calibrations, other types of alerts, because it will be related to maybe one large explosion, and so we will not have the same criteria to scale up the early warning levels. Yeah.
Thank you.
Okay. So if there are no other questions, well, once again, many thanks to you two. Muchas gracias a todos y a todas por estar aquí. Y pues sí, van a estar aquí todavía una semana. Vamos a instalarla el día de mañana, pero si tienen preguntas, pues con mucho gusto trataremos de organizar una. Y también hay galletas y café afuera por si quieren discutir ahorita. Tal vez mejor.
Okay.
Gracias.
Gracias.